Okay, let's go through this practice test fairly quickly. Should be a review. Most of these problems I pulled practically straight from the video lectures and concept workshops, but it helps to kind of pull it all together in one setting. So use the graph to find the sine leading coefficient. So here's our graph. The sine of the leading coefficient. You recall our general formula here. Y equals ax squared plus bx plus c. A is our leading coefficient. And what do we know about the sine of A, how it affects the graph of the parabola? If it's positive, it opens right up. If it's negative, it opens down. Our parabola is opening down, so the sine is negative. My pen's kind of pooping out on me. This is like the second or third time I tried this, so hopefully we'll be able to make it through. The vertex. So the vertex is right here, and it is the coordinate 1, comma, negative 3, right? X, comma, y. 1, comma, negative 3. Axis of symmetry. Again, we have some symmetry going on here. That is, I could put a mirror right here on this, and it would reflect perfectly on the other side. And so axis of symmetry is going to be x equals 1. It's always x equals whatever that x coordinate is when the parabola opens up or down. Intervals where f is increasing. So here's our function. It's increasing from, if we go left to right, all the way from negative infinity all the way up to 1. And it's decreasing from 1 to what? Careful here. 1 to infinity, not negative infinity, because we're looking at the x. All we care about is the x. As x goes to infinity, this thing's decreasing. Okay, part F, if f of x and f of x equals ax minus h squared plus k form, we want to write it this graph in that form. So what do? Let's first start by plugging in what we know. We don't know what a is. X and f of x stay the same, so x minus, remember our vertex is right there, right? And this is h, comma, k. So h is 1, k is negative 3. So x minus 1, then plus negative 3 would be minus 3. Okay, now what we want to do is find a point on our graph. And this is an easy one right here at negative 4. So 0, negative 4 is a point. Again, so that's the point 0, negative 4. And you could pick any point. 0 always makes the arithmetic come out a little bit easier. So here's my x, and here's my y, or f of x. So f of x is negative 4. I'll have negative 4 equals, I still don't know what a is, a, and then x is 0. I left off my squared here. Minus 1 squared minus 3. And again, our goal here is to solve for a. And so we'll have negative 4 equals, so 0 minus 1 is negative 1. Negative 1 squared is 1. So we'll have a times 1. We'll just put a minus 3. Solving for a, we're going to add 3 to both sides, and we'll get a equals negative 1. So that's not our final answer. We're going to take that and plug it into that equation, and that would be our answer. So f of x equals negative 1, x minus 1 squared minus 3. Okay. Now part G, we've got a couple options. The easiest way, I think, is just to use this form here and square it out and just solve for f of x. So if I do that, I'm going to square that out first. Let's leave negative 1. X minus 1 squared. Remember, we're doing x minus 1. I'll write this out. You don't have to if you can do it in your head. But make sure that you are foiling that out. You don't just want to square the x and square the minus 1. So leave that negative 1 out there. So x times x is x squared minus x plus 1, and then minus 3. Be careful with order operations here. I'll leave the minus 1 out here one more time. Combine some like terms right here. X squared minus 2x plus 1 minus 3. And again, I should have been putting f of x on all these. I've got myself a little cramped here. So f equals, and then we can distribute our negative 1 through. Negative x squared It's going to be plus 2x. Now it's going to be minus 1, and then I'll have a minus 3. I can combine those to give me a minus 4. So I know you can do a lot neater than I just did, but there you go. Okay, solve the quadratic equation, give the exact value. No decimals. A lot of you are still going to want to give me decimals. You'll get no credit for it. So make sure that you use the quadratic formula on this. We got to do at least one. It used to be, in the old days, I'd give you 20 of these. You'd have to do all of my quadratic formula or factoring. Now I'm giving you one. You got to show me you can do this quadratic formula on one of them. So here we go. So let's write it down first. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. I recommend putting this on the note card, and then when you do it on the test, write it down. Students who write this formula down on the test rarely miss it. Students who don't write it down usually miss it. Write it down. I'm close to making it just a requirement to write the formula in every time you have to use it, because students who do that rarely make mistakes. Okay, now we're going to plug in. So we got A, B, and C. We can label these off to the side if we need to. I think most of you are good at labeling these. So A is 3, B is negative 4, C is negative 1. Just be careful with your signs. Make sure the sign carries over when you plug it in. So negative B, so I'm going to have negative negative 4, which is a positive 4, plus or minus the square root. I'm kind of a believer doing a few things in your head. Keeps the arithmetic down a little bit. So B squared, I can do negative 4 squared in my head, right? I get 16. Now what a lot of you would do is you'd put negative 4 squared in the calculator like this, and you get a negative 16, right? Which is wrong. You know that's wrong. We got to make sure we put this in parens if you're going to use it the calculator, okay? Which you should get a positive 16. So b squared minus 4ac. So minus 4, we can do this arithmetic in our head. 4, here's 4 times a, which is 3. So we got 12 times a negative 1. So it's going to be plus 12. All over 2 times a, 2 times 3 is 6. So we've gotten a lot of the arithmetic out of our way. If we didn't, we'd have a lot of stuff to worry about. Okay. So I'm going to have 4 plus or minus the square root. 16 plus 12 is what? 28? All over 6. Now I'll be honest, I'm okay with the answer being left this way, but Course Compass would not be. If you're checking your answer, you need to be able to simplify this all the way down. So we take this 28, and we find the perfect square that's kind of nestled inside of 28. If I did that up here, 28 factors into 4 times 7, right? So when I take the square root of 4, I get 2, so I'm left with 2 root 7. So this gives me 4 plus or minus 2 root 7 all over 6. I can do a couple more things here. I mean, the only reason I really would want to do that is if I could cancel out. I've got a common factor of 2 in the top, so I can factor that out. So I'll get 2 plus or minus root 7 all over 6. Now I can cancel that 2 into the 6 to go 3 times. Now you could have done it from here to go straight, but most people mess that up. So it's good to go ahead and factor that out. So this is the final completely reduced answer. But again, I would take either one of these. Okay, maybe I'll give you an extra point if you went all the way down to the reduced form. And you can always check this on the calculator. So on the calculator, put 2 plus root 7 and divide all that by 3. Make sure you put the top in parens. Look at that number and see if it is the decimal equivalent when you use the graphing method to solve. 2 minus root 7 over 3. Okay, use the vertex formula to find the vertex and use this to help sketch a graph. So we need to find the vertex. We have x equals negative b over 2a to give me the x coordinate of the vertex. And then whatever you get for that x, just plug it in and find out what y is. Okay, so again, we have negative b. So in this case, b is negative 4. So we have a negative negative 4, which is a positive 4, all over 2 times 2. So we get 1 for the x coordinate. How do I find y? There is actually a formula for it, but I find it's much easier just to take this and plug it in for the x to find out what y is. So what is f of 1? So we have 2 times 1 squared minus 4 times 1 minus 3. You would not need to show this work at all. I know you can do this in your head. So 1 squared is 1, 2 times 1 is 2, minus 4, minus 3. So 2 minus 4 is a negative 2, minus 3 is a negative 5. So f of 1 is negative 5. So there's your vertex. 1 comma negative 5. I use that to help me graph. So I go 1, negative 5. I know I've got a line of symmetry right here, so I expect to see that drawn. And then just pick one other point. The easiest one to pick is generally the y-intercept. Unless that y-intercept's something like negative 30, you wouldn't want to pick that. Choose any other point that kind of makes sense. So when x is 0, y is negative 3. Pop that right there, and then do your best to draw a nice looking sketch of a parabola. And we can use symmetry here. We know that this point here is going to be there because we know it's symmetric. Right? And that's good enough. It doesn't have to be perfect on this one, okay? I want a sketch of a parabola. Okay, use the find the x-intercepts for number 3 above. Use any method. Round to the nearest hundredth if needed. Do these values make sense in light of your graph? Okay, so we could use quadratic formula to find out where these cross. And it looks like my graph got all messed up over here. Because the vertex was down at negative 1, 5. I'm not sure how all that happened. Thing kind of got slid around. Let me just sketch that back on. Okay, so it looked better when I first did it first. Okay, so what are these x-intercepts here? And we can use quadratic formula, but I'm just going to use the calculator. If I pull my calculator up, okay, so we're going to put in 2x squared minus 4x minus 3. Let's just do a zoom 6. My graph looks reasonable to that. So let's find these intersections. Now I need to find, put a 0 in here and graph that. You can't see it, but it just drew a line right here. So now I do second trace, number 5, and then enter, enter, enter. So one of them is at negative 0.58, right? Okay, but we have another one too, don't we? So I need to find it. So second trace, number 5, enter, enter, but this time on guess I have to scroll over until I'm a little closer to this one, and then press enter again. So I get 2.58. Okay, and so I should have used the approximately equal to here. And do these make sense in light of our graph? Does this look about where our graph was? Yeah, that looks reasonable. You know, about in between negative 1 and 0, and in between 2 and 3. My graph was just a sketch, and this graph here probably wasn't as good as my first one. Okay? So this does make sense. Does this make sense? Yes. Now, oftentimes I'll put this on the test, and people will get crazy x-intercepts. They'll get none, or x-intercept of 52, and they'll say, yes, it makes sense. Really make sure you look at that and make sure it makes sense. I mean, whatever numbers we get here for the x-intercepts should be about what we got when we graphed it, when we did our quick sketch. Okay? This is one of the most missed ones. Use the graph to solve each equation or inequality. Right? The inequality enters in set builder or interval notation. Okay. So where is f of x equal to 0? So here's our function. This graph here, it equals 0 right here and here, at negative 1 and 3. So we'll say x equals -1, comma, x equals 3. Simple enough? Where is this less than 0? So where is the graph below? Here's my 0 line right here, right? Where's my graph below that line? What's below it? Right through here, right? In between -1 and 3. And it's a strict inequality, strictly, so I do not put the brackets on. I use parens. Or in set notation, or an double inequality, you can say x is less than 3 and x is greater than 1. You can do one or the other. Now, where's this greater than 0? Well, it's greater than 0 all the way up here, right? Above this line, in the kind of the bold red I'm trying to draw. So from -infinity all the way up to the -1, we pick back up with 3 to infinity. Once you get this, this part is not that bad. I mean, some things that we do, once you get it, it's still kind of tedious. But this usually ends up being pretty good by the end of the semester. We end up having something like this in every section. So hopefully by this chapter you will start to kind of see how to read these graphs. Okay, write the equation of the graph. The graphs are translations of one of the following. And so the graph that I give you will either be a translation of y equals x squared, which is a parabola, y equals root x, which is half a parabola, or y equals absolute value of x. So that, for many, is kind of confusing. I mean, so make sure you know that the original graph, what it would have looked like. So, you know, parabola, oops, I can't see that. So if it were y equals x squared, it would have started off right here. This isn't a parabola. Y equals root x looks something like this. Half a parabola going to the right or left. And then absolute value is a v starting the same place the parabola does, at the origin, 0, 0. Okay? Quick little sketches of what they look like. You can always graph those in the calculator and see what they look like. Okay, so what have we done here? We have shifted over to the right 2. So what does that mean my equation is going to be? So that means I've got absolute value of x, and we're going to the right 2, so it's -2. That's the one that's kind of counterintuitive. And then I go up to 3, right? Plus 3. And that's it. I think it's a 5-point problem on the test, so not hard to do, but make sure you get these signs right. You won't get credit if you get the signs wrong. This is kind of an all or nothing on this one. Okay, use the accompanying graph of y equals f of x to sketch the graph y equals f of x minus 1 plus 2. So we had one similar to this on the video lecture and on the concept workshop. Again, these are pretty easy. If you're going to miss one, don't miss this one. Because what does this mean? F of x minus 1, that means I'm going to shift 1 unit to the right. So all these here are going to go 1 to the right. And then up 2. Right? So let me just redo my dots. And then sketch your graph. And that's it. Again, you need to know how to read these. Put an example on your note card, if it helps, on how to see how these move left and right. If this had been f of x plus 1, I would have gone 1 unit to the left. Okay? Okay, for the function below, find the following: vertical asymptotes, horizontal asymptotes, domain, and the range. Okay. And don't worry about the points. This must have been a 5-point problem from a test that I took. Okay, so the vertical asymptotes occur when? Looking at the function. We know what they kind of look like, right? They're sort of imaginary vertical lines. But they occur when the denominator equals 0. So just remember that. Write that down on your note card. The vertical asymptotes occur when the denominator equals 0. So if you can't look at this and see when it's going to equal 0, just set it equal to 0. X plus 3 is 0. And solve for x. Subtract 3 from both sides. We get x equals -3. Okay. So there is our vertical asymptote. Now horizontal asymptotes are a little trickier. There's a calculus way to do it and an algebra way to do it. We're going to look at it the algebraic way, of course. When you look at the calculus way, you end up involving limits to infinity, which is what the horizontal asymptotes are. But the algebra way to do it it's pretty simple to say. It's harder for me to kind of write down as a pattern, but I can tell you how to figure this out. What you do is you look at the x's in the top and the x's in the bottom, and you're looking at the exponents. So these both have an understood exponent of 1, right? If those exponents are the same, if they're both 1, if they're both 2, if they're both 3, if they're both 4, if they're both 5, etc., 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 right? Your horizontal asymptote, this is if we're looking at the highest x, so we have more x's, you look at the one with the highest exponent, you compare those. The horizontal asymptote is always y equals, and it'll be this number, which is a 1, over this number, which is a 1. So y equals a 1 over 1, which is 1. Let me give you another quick example. What if we have y equals 3x squared over 7x squared minus 10? What would my horizontal asymptote be? These are the same, and so my horizontal asymptote is just y equals 3/7. Make sure you put y equals, don't just put 3/7 there. Now, if they're different, well, I shouldn't say different. If the bottom has a higher exponent than the top, it's always y equals 0. Okay, so if I had y equals x over x squared minus 9, my horizontal asymptote would be y equals 0. And there's a very good reason why this happens. As x gets bigger and bigger and bigger, the whole thing ends up going to 0. Okay, in both directions in this case. Now, if the top is bigger, you end up with slant asymptotes. And we're not going to do those in here. It involves long division, and we're not going to worry about those. So again, if they're equal, it's the coefficient over the coefficient. If the one on top is smaller, it's always 0. Otherwise, there are none. Okay. And you can go back and watch the video over that in an earlier lesson for a fuller explanation. Okay, the domain. Remember, domain answers the question, what can I plug in for x? And it's sometimes easier to kind of look through the back door and say, well, what can't I plug in? And look here at the denominator. We focus in on the denominators because we know when we're dividing, we can't divide by, 0. So what number, when I were to plug it in, would give me a 0 in the bottom? And we've kind of already found it out, right? It's -3. So my domain is everything, all x, such that x cannot be -3. And I'll be honest, in this class, I'm okay if you just say everything, all real numbers, but -3. Now, if you go on to higher maths and the calculus, they'll expect you to be able to write this in some sort of set notation. Okay, range is a little trickier. So the range answers the question, what can all the possible values of y be? Okay, and it's sometimes easier to look at the graph. So if I were to graph this, so y equals, let me clear everything out. And so in the top, we're going to put x minus, I forgot my parens, didn't I? Parentheses, x minus 1 in paren divided by x plus 3. Okay? Now if I do a zoom 6 on this, the question is, are there any values for y that I'm never going to hit? And yes, there is. There's a value for y I'm never going to hit. It's similar to the value of x I'm never going to hit. It's never going to hit, in this case, the y asymptote. The line gets closer and closer to it, but never actually reaches it. So my range, in this case, is all y's such that y cannot be 1. Now, in some cases, it can be the y-intercept, and it can be everything. We're not going to see a lot of those, so I don't want to focus a whole lot on that. But if you go into calculus, you'll see a bunch of weird things, how these functions can behave. Okay, given the graph, find the following. Let's find the turning points and then intervals of increasing, decreasing. So really nothing new, maybe a new word, turning point. Hopefully that visually will make sense to us. Turning point is just where the graph happens to change directions, right here and right here. So we have it at, what is that, negative 3, 4. And at negative 1, 0. Those are the turning points. Simple enough, right? So where is this increasing, decreasing? But we do a lot. I think every chapter so far we've had increasing, decreasing. Make sure you understand how to figure that out. So where's this graph increasing? It's increasing all the way right here from negative infinity all the way to negative 3. And then from negative 3 all the way to negative 1, we're decreasing. But then we pick back up with increasing. Right? So union, what would we say? Negative 1, comma, infinity. So again, I'm going from increasing, and all I care about is the x. I'm looking at the x intervals. So it's increasing from negative infinity all the way up to negative 3, and then from negative 3 to negative 1, we're decreasing, and then from negative 1 all the way to infinity, we're back to decreasing. So again, increasing on this interval, decreasing, and then back to increasing. Given the graph below, identify the horizontal and vertical asymptotes. Okay, so what would the vertical asymptote here be? Well, here they are right here, right? So we're going to have x equals negative 3 and x equals a positive 3. How about the horizontal asymptotes? They're not explicitly drawn on here, but we should be able to kind of see it's this y equals 0 in this case. Now this is a case where actually the graph crossed the horizontal asymptote, and they can do that sometimes, like in this one. So it doesn't ask this, but I could certainly ask for domain. What would domain of this be? All x such that x cannot be plus or minus 3, right? The graph can never cross the vertical asymptote. What would the range be? It looks like the range is going to be all real numbers. Again, the range is all my y's. And it can hit every single y. So I've got a graph starts from negative infinity, goes all the way down to infinity. So it's going to get all the y's down there. This one goes up to infinity, and so does this one, and we even get the value where it crosses the y right here. So the range would just be all real numbers. We'll say all real numbers. Okay. A baseball is dropped from a stadium seat. Its height, s, in feet after t seconds is given by s of t equals 75 minus 16t squared. What is the initial height of the ball? So again, t is the number of seconds after it has been dropped. So the initial height is when t equals 0. So at t equals 0, I'm trying to find s of 0, right? 75 minus 16 times 0 squared, which is 75, and we are in, what, feet? That's it. Estimate to the nearest tenth of a second how long it takes for the ball to hit the ground. So s is the height, so what does that mean for it to hit the ground? That means that the height is 0, right? So now we say 75 minus 16 t squared equals 0. So make sure it's clear when you plug in for s and when you plug in for t. Because here we're looking for the seconds. And we can just solve this out, right? We can add 16t squared to both sides. We get 75 equals 16t squared. Divide by 16. And so I'm running out of room here. Let me come back over here. So I've got 75 divided by 16 So I'll have t squared equals 4.6875. So t squared, I've lost my pen, I don't want to restart in the middle of the problem, equals 4.6875. And I recommend not rounding until the very end. So don't say 4.7 and then square root that and get a decimal. It ends up, when you start rounding upon rounding, it just introduces a lot of error. Okay, so let me make that font a little bigger here. Well, that's okay. I think you can read that. And now let's take the square root of that. So the square root of that is 2.16. So t equals 2 point, and we're rounding to the nearest tenth, so that'd be 2.2. 2.2 seconds. Now we could use the calculator to do this from the beginning without solving that. Because I didn't have a middle term, it was pretty easy to solve for t. But if I had a middle term, like if it was 75 minus 15t minus 16t squared, I would. And that middle term, if you take a basic physics class, comes from some sort of initial velocity. If I threw it down with some velocity, if I throw it up with some initial velocity, that's where that term would come from. Again, all we do is press y equals, and let's put in 75 minus 16. We have to use this x key, whatever the independent variable is, x squared. And I plop a 0 in. Whoop, wrong one. Now if I do a zoom 6 here, I may not be able to see what's going on completely. Looks a little weird, doesn't it? I can make this window a little bit friendlier. Now I can certainly find it right here. So if I can see that intersection, I'll be able to find it. But let me just show you. We know that t can't be less than 0. And then we can say x max. Maybe we don't expect it to take any more than 5 seconds to fall 75 feet. That's a lot of time. If you have a sense for your domain, your x min and x max, put those in and then press zoom fit. It'll kind of find the best window for your graph. It doesn't always work, but with polynomials, it usually does a pretty good job. Okay? And it did. So I can quickly see it looks like around 2 seconds. I'm pretty sure I'm going to be right on this. So second trace, 5, and then enter, enter, enter. And sure enough, we get the same thing we got when we did it by hand, about 2.2 seconds. Right here. Okay? After peaking in 1970, school enrollment in the U.S. fell during 1970s and the 1980s. The total annual enrollment in millions in U.S. elementary and secondary schools for the years 1975 to 1996 is given by our model, and the model is E of x equals 0.058 x squared minus 1.162x plus 50.604. X equals 0 corresponds to 1975, x equals 1, 1976, etc. So what was the enrollment in 1975? So what value would I plug in for x? Well, this one should be really easy. It tells you x equals 0 was 1975. So I'm just going to find what is E of 0. And this one, you shouldn't even need a calculator, right? Because when I plug a 0 into the first term, it goes to 0. Second term goes to 0. So I'm just left with, whoop, that didn't turn out too good, 50.604. We're in millions. So again, a little over 50 million. 550.64 million, not millions. For this period, when was the enrollment lowest? So again, we need to find, we should recognize this here being a quadratic, so we could find the vertex of our parabola. You could use the vertex formula, or we could just plug it in the calculator. I'm going to encourage you to actually use the calculator on some of these. Okay, sorry about that phone call. So I kind of forgot where I was. We're going to put this equation in. So y equals 0.058 58x squared, and I know you can't see this top of the screen. I'll bring it back down in a second, but you should be able to type that in. Minus 1.162x plus 50.604. Pull it down so you can see what I put in. And I'll also take a second glance to make sure there are no typos. 1.162x plus, okay. And what are we even looking for? Oh, we're looking for a graph of this. So we know that it goes only between 1975 and 1996. So when I press window, I'm not going to put 1975 here because remember, 1975 corresponds to x equals 0. So 0 is 1975. So 1996 would be, what is that, 21? 21 years after 1975. And then do a zoom fit. So it's worth knowing. I mean, there are a lot of tricks on the calculator that really aren't worth knowing a whole lot because honestly, you can, you'll use it once or twice. But being able to do that, you'll use all the time because oftentimes they'll give you sort of a range of acceptable values, acceptable years, and things like that. Okay, so there's our graph. So we're looking for this minimum value. It falls somewhere in this range here. Sometimes I'll click on window just to see what kind of values it picked up. So 0 to about 51 million. Okay, so I'm going to find the minimum, and again, you may not be able to see that. Press window again. Okay, so I'm going to go to second trace and find the, looking for where it's lowest, so the minimum, which is number 3. It's going to ask you 3 questions. Left bound, so just get anywhere to the left of the minimum. Make sure I'm up on one of those rises there and press enter, and then get anywhere to the right. That looks good. Press enter and then press enter again. And there we are. So the minimum, it happens at x equals 10. So 10 years after 1975 would be 1985. It's 1985. And this is when we had about 44.784 million students. Okay, so there's the first part, kind of I, and here's I. In what year was the enrollment 49.5 million? Okay, so what are we really solving here? We're really saying 49.5 equals that whole right side, 0.058 x squared minus 1.162x plus 50.604. You know me, I'm going to turn the calculator to do this one. I am not going to try to solve that with quadratic formula. You'd have to set this to 0 and use quadratic. Not worth it for this case. You ought to be able to do it. I mean, the numbers just get big. I already have this equation in, so I'm going to put, rather than 0 in for y2, I'm going to put 49.5. So I'll pause, kind of let you see what I have in. Now when I graph it, I've already kind of picked my best window. Okay, so it looks like it crosses it twice here. And so I'm going to go to second trace, looking for intersection, number 5. First time I just press enter, 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 and it found this one over here. So at about 19, so 19 years after 1975 would be 1994. So that's one answer. So, and in about 1994, but we have another answer too, right? So second trace, number 5. Enter, enter, and rather than scrolling, you can just take a guess at it. You know, maybe looks like around 1 or 2. We'll say 2. And actually occurs at 1. So 1 is 1976, right? So in these 2 years, the enrollment was 49.5 million. So not too bad. Not too bad.